what we had last time was that any periodic function f of x, if the function keep repeating itself over a period of 2 pi, from minus pi to pi, it's periodic, it keep repeating itself, using Fourier series, which is basically a bunch of cosine and sine multiplied by constant, you can express that periodic function in terms of the cosine and sines. And so the homework problem that you had is basically saying, giving you an f of x and asking for the Fourier series. He's asking for what is the an and bn that you would, not just an and bn, you have to multiply them by the cosine and sine and basically say then my f of x is those guys. It's those terms, right? And so to get those a naught, an and bn, it's simply this integration. Right? Whatever f of x is, you integrate and you get the a naught, you multiply by cosine and you integrate, you multiply by sine and you integrate. Okay? And so we had an example last time, periodic function, and we said that sometimes you get lucky because the function is odd or even, so one of the coefficients will disappear. The an could be 0 or the bn could be 0 depending if it's even or odd. And so you don't usually do the 3 integration, you just do one of them, for example. And you get your coefficients, and sometimes some of the coefficients will die. So not all the bn will survive. For example, you know, it could be b2 and b4 and b6 will die, and you get only b1, b3 and b5, or the opposite. So when you say then the f of x is b of n multiplied by the sine, not all the sine will survive. Only sine x, sine 3x, sine 5x. Why? Because the b2 was 0 and the b4 was 0 and the b6 was 0. Only the b1 and b3 and b5 multiplied by the sine and the sine 3x and the sine 5x survived. Okay? And so this series expand forever. But sometimes you don't really have to add forever. Sometimes, you know, after few terms, the number become very close. The Fourier series that you add, the 5 terms that you added so far, will get you very close to your function. Alright? That's the promise, however, anyway. It's that we don't really need to add infinite number of terms. The promise is that maybe 20 will do, maybe 10 will do, maybe 5 will get you pretty close. Right? And we finished last time by basically saying that not every function will be periodic from 0 to 2 pi. This only the sine and cosine. That's why they will a perfect match for us. But what if the function we are trying to get the expansion, the Fourier expansion, is periodic over, rather than 0 to 2 pi, 0 to 2l, or basically from minus l to l? What do you do? And so it turned out that it's not a big deal. It's the same thing except the integration, rather than going from minus pi to pi, that was the period, minus pi to pi. Now it's minus l to l. And instead of 1 over 2 pi, it's 1 over 2l. Okay? And remember here there was cosine nx and sine nx. Now you will have cosine n by x and sine n by x over l. So basically what will happen is that you will end up with this pi over l, pi over l. That's the change, right? And over here the same thing for the integration. So if the function is periodic between 0 to 2l or minus l to l, you just have to follow the new recipe, do the new integration, right? And the same rules apply, that if it's f of x is even time even, will this guy survive? But for example, this guy will disappear, right? If it's even between minus pi to pi, it will also be even between minus l to l, right? Very good. So that's what he's trying to say over here, that odd function and even function, if f of x that we are trying to expand is even or odd, one of the terms will disappear and make our life easier. Half the work. We'll only do half the work. Alright? And so here is an example. And so this function that basically go to k between minus 1 to 1, this is periodic over, what's the period? Look at this graph and tell me.
2.
No, If it's 2, then it will have to stay like this forever. But look at this, it basically die over those periods. So the period is really, it's as if it's from minus 2 to 2. That's the period. So the period is actually 4, not 2. Okay? So when that's important, because when you do the integration, when you follow those formula, you have to put your eye on the L. So it's not the integration from minus 1 to 1, it's actually from minus 2 to 2. Eventually it will go down to minus 1 to 1, because if I'm integrating f of x from minus 2 to 2 time cosine, why the integration will boil down only to the minus 1 to 1? Because f of x is 0 from minus 2 to 1 and from 1 to 2. So basically then, yes, the integration is supposed to go from minus 2 to 2, but f of x is 0 for the first part of that integration, right? But still, you got the 1 over L, and the L is 2. The L is 2 because the period is 2L, which is 4, all right? So there is nothing new over here. You just follow the formula and do the integration. You get your AN, and for the BN, look at the BN. Is this function is odd or even? Right? Even, because the function here is equal to the function there. Right? F of x is the same as f minus x. So BN is 0. Even function multiplied by the sign, what would be the result? Odd. Even multiplied by sign, the result is odd. And so integrating an odd function from minus L to L is 0. Right? So that's why you don't do the BN. You just say 0 because f of x is even. Right? So here is f of x. Questions? So you have two homework problem, one basically that go from minus pi to y, and the other one go from minus L to L. Okay? So you just use the two formulas to get the two expansion. Questions? Very good. So the Fourier series, it basically work very similar to the Laplace, meaning that if you are supposed to get the Fourier expansion for a function that look like two things, f1 plus f2, you can get the Fourier function only for f1 and then the Fourier function for f2, and then add them together, for example. Why? Because that summation will get divided over the two. It's almost like an integration too. When you think about it, actually, the Fourier series, when you look at those formulas, it looks as if it's the limit for an integration. Okay, we'll see this in a second. All right. So if I'm having a function like this, f of x equal x, this is how it will look like, right? That's an odd function, right? Fx plus k, how it would look like? It will be like f of x, but it's lifted k. So if k is pi, you will end up hitting pi over here, for example. So this is odd. How about this guy? Think again. Think one more time.
It's neither.
Right? You see, this is why this is odd. Because you come here 1, you come here, it's minus 1.
And it goes through the
Right?
origin.
Yeah, that's not the reason. But anyway, it's because if f of x is minus f of minus x, but you come on this one, and over here I get, say, 2k, and here I get 0. Obviously it's not even, it's not odd. That's so sad, because
Then you have to integrate both.
right now I have to do the 3 integration. Does this help anyway? That if you would like to get the Fourier of f1 plus f2, just give the Fourier of f1 and then get the Fourier of f2 and add them together. Does this help us anyway here?
You could.
How does that help? I don't want to do the 3 integration.
Well, you could. Could you do the Fourier of x.
Excellent.
And the Fourier of
So you should think about x plus k as two functions. One of them is x, which is odd, doesn't have any a naught or an, just the bn. And I could look at k as a constant. And by the way, the k actually doesn't have bn, of course, because it's even to start with, right? A constant, f of x equal 5 or equal pi, you go here it's pi, you go there it's pi. So of course it doesn't have bn, but also doesn't have even, doesn't have what? It will not have bn because it's even. It will also will not have an, it will just have a naught. Actually the expansion is just the constant, right? So basically you don't do anything, you just, it's the constant. All right? So if we can with a simple trick split our function into an even or odd function and a constant, that save a lot of time. So that's what he said over here. So you got this function f x equal x plus pi. That's how it will look like. X plus pi. F of x will look something like this, okay? But going through the origin. And x plus pi, that's why it shifted up by a pi. And so you would look to this and say, that's x plus pi. Let me just get the Fourier for x, the Fourier for pi, and then add them together. Okay, f of x obviously is odd, you only get the bn, and f of pi you just get constant, get a naught. That's it. So here how it works. So for bn, first of all he's doing f of x. Okay. So this f1 of x, which is x, you only get the b of n. He's saying how the an is 0, and you do this, and that's the bn. All right. And the constant, look at this, f of 2x equal pi. What happened? It's simply just pi. There is no integration to start with. A constant, you expand it as a constant. Got it? So you only do the odd function. So there is this pi and there is those guys. So back again now to the problem that we solved earlier. This and this. We could have looked at this problem and think this is not the function. We could actually make it something like this. It doesn't really help that much, but you can look to it as something like this. It's a constant which is k plus 2, and on top of it that function, and that even function will reduce those guys. Okay, but it didn't really help that much, because to start with this was an already even function. You do that trick when you don't want to actually do through the 3 integration. You want to turn your function into an even or odd function.
So the k over 2 is just part of that equation, like when you write out the final equation, it's just...
So that k over 2 came from the a naught.
Okay.
He did the a naught and he ended up getting k over 2. But I'm also saying that this blue function, rather than expressing it as 0 and k and 0, we can express it as minus k in this place, and plus minus k over 2, and plus k over 2 in here, and then minus k over 2, plus a constant, which is k over 2. So the constant will be like this, and this would be the other function. But it doesn't save that much time, because in this example, because this is already even function, we already didn't have to do the pn. And the saving that you'd say, but see, we now we have to do a naught, and if you add it as a constant, you don't have to do a naught. But look at the integration is much easier now, going to 0 and 0, here and here. So there is not much saving, that's why he didn't do it. But of course this is a lot of saving. Alright? Questions? Alright, so he got all the terms. Alright, and again the promise is that you don't have to do all of them. So of course if you have only one term, you will not really be on top of the curve. this is S1, this is S2, S3, and you can look at S20 after 20 curve. See how close they are? It's pretty close to the straight line. Alright? Questions? So again, to recap, there are two formulas, one for periodic function from minus pi to pi, one for periodic function from minus L to L, but also there is this kind of extra help that if the function is not even and odd, by splitting it, you can basically manage to put it in an even or odd format that saves you a lot of time. Okay? Very good. So now let's see an application of those Fourier transformation to solve an oscillation problem, first oscillation problem. So before we see the example, let's remember that a linear ordinary differential equation mean that if y1 is a solution of that equation, y1 equal cosine t, for example, and y2 is a solution, y2 equal sine t, then adding the two of them, cosine plus sine, for example, will also satisfy the equation, will be a solution. That's the point behind linear equation. Okay? So why is that useful? You will see in a second why it's useful. Coupling with a Fourier expansion, that's a very powerful technique to solve first oscillation problem. So a first oscillation problem, this is not just mechanical engineering, it's also could happen in electronics. So a system like this or this will generate a second order equation like this. Okay, mass time y double prime plus c, that's the coefficient of the damper, then coefficient y prime plus k, that's the spring, time y equal to the force acting on the mass. Okay, and let's leave this for engineering, but you will end up with second order system similar to this. Alright? So why this equation is like this? Well, here is the free body diagram. If I have this mass stuck between a spring and a damper, the moment you take this mass and take it up and down, any y deflection will cause a force in the spring. Let's take it down in the plus y direction. If I take the mass and shift it y down, I will get a force ky up. And depending on how quickly I'm moving down, I get a resistance force cy prime up. Right? On top of that, you have the force that's moving this mass, r of t. So Newton's second law will be the mass times the acceleration equal to the forces. If they're pointing up, will be negative. If they're pointing down in the plus direction, will be plus. That's why you'll end up with this equation. Okay? So this equation is second order, but is it linear? Y double prime, he just plugged the mass equal 1 and the k equal whatever and the c, so you end up with basically y double prime plus 0.05y, 05y prime plus 25y equal RT, the force. Is this equation linear?
Don't think we know yet.
Why? What will make the equation non-linear? Like the problem we had in the exam. Why it was non-linear, the MEC problem?
It's linear. It's the slope of -1 and +1 and intercept of.
So for why the exam problem was non-linear?
This n was raised to.
Right, the unknown that we are trying to solve for was raised to a power. Right? Second order, first order, that's non-linear equation. So those guys, yes, there is a second derivative. Jason's right, this is linear because I don't have y prime square. I don't have y multiplied by y prime. I don't have y multiplied by y double prime. I don't have y square. I don't have y double prime, the whole thing to power 3. So I have the derivative of the unknown, but still they are standing by themselves. That makes it linear equation. Therefore the solution, if I have one solution for this one, and I have another solution, this adding the two of them would be a solution to will satisfy the equation. So when I'm trying to find a solution to start with, who said I'm having infinite number of solutions that I would like to add? Well, it will come from this. See it. He say the r of t, the force is basically this guy. It's periodic. Okay, it's periodic, and those are the equation. So r of t would look. Let's have a bigger picture. So r of t is basically You can see the slope is plus 1. It will be basically plus t, and because the intercept is pi over 2, then this line is t plus pi over 2. This guy, the slope is minus 1, so that's why it's minus t plus the intercept. Any straight line, you can write its equation as ax plus b. Okay, y, if it's a straight line, then y is, in this case, not ax, at plus b, because the x-axis is t. What is b? What's b? I can't hear. Right, it's basically the part that you cut the y-axis at. And this is the slope. Very good. Right, so that's why this is minus t plus pi over 2, and this guy is plus t plus pi over 2. And if the slope is 2 or 3, it will not be plus t, it will be plus 3t, plus 4t, plus 0.5t. Anyway, so here is the equation, the second order differential equation, or the differential equation, and here is the function. So, because this guy is periodic, what can we do with it, since we are in Fourier Expansion chapter? You can split this guy into bunch of cosine and bunch of, actually, because it's, what do you think, is it even or odd?
Well, it's even, but it has a constant. Wouldn't it be? No, maybe not.
How we can tell it's even or odd? Let's go at pi, check the number, go on minus pi and check the number. If they are the same, then it is even, right? This function is even. Say that again. So if some, sometime you will have like the same slope and it will be odd, like this. This is an odd function.
Because it doesn't change direction.
So you're saying an odd function will always.
I understand you would count like
So anyway, the rule is really very simple. I don't really worry about checking the slope. I just ask myself, is f of x is equal to f minus x? If it's mirror image, I'm done. Even mean a mirror image. All you have to do is basically put a mirror in the middle and tell yourself, does the right hand side look like the left hand side? It does. Therefore, even. Therefore, what disappeared from us?
The sign.
All the sign disappeared, right? It also happened to have so anyway, so the others also, the 2t and the 4t also disappeared. So anyway, here's r of t, or in general r of t is basically 4n squared over pi cosine nt, right? And the n is 1 and 3 and 5 and so here is the trick. Because this function is linear, and because the input function, it can be considered as bunch of cosine, we can replace this guy by those guys. So it's as if the force is not just one force. It's as if the system is responding to a bunch of cosine at the same time. Okay? So if we know the solution for one of those cosine, and the solution for the second one, and the solution of the third one, if we know the solution of the function to each one of those cosine, and we do, it's very easy. I know the solution for the cosine, but I don't know the solution for this weird function. No one had the solution for this, but we have the solution for a cosine. It has been done before. So then the actual solution for the R is the solution for each one of those guys. Let's add all of them together. So then that's the power of the Fourier expansion when it comes to a system like this. Because whatever, as long as this function is periodic, chances are, if it's a mechanical system and you are basically subjecting it to the same input over and over and over and over, you can expand it into Fourier and get the solution for each one of the cosine and add them. Alright? When I was doing my master, actually, so I had my acoustic system basically responding to a frequency input bunch of harmonics, basically. I'm sending sine waves. So not just R of t that's periodic. No, I am actually giving him sine waves. All right, a different frequency, because basically I'm trying to simulate a source that's basically working a different frequency. But surprisingly, the solution wouldn't add because what? What do you think? Why the solution didn't add? The solution, the final solution, is not basically let's add this guy plus this guy plus this guy plus this guy. It's because this one added up, we can add this one because it was linear. So obviously mine was because I was solving Navier-Stokes equation. And Navier-Stokes equation, fluid mechanics, you know this when you take experimental fluid, it's non-linear. So basically the solution wouldn't add. Alright? Very good. So this work only if the system is linear. Alright? If the equation we are solving is linear. So here what he's trying to say, basically. It's saying let's expand RT. So here's the RT, the equation is like this with bunch of cosine, and then you say for each one of those cosine, the solution should be, if you have a second order like this and you are sending a sinusoidal, in general it's an cosine nt plus pn sine nt. That is the solution. Right? And so if you basically plug those guys in here, if you assume the solution, you just assume the shape of the solution. You don't know the an and you don't know the bn, but basically you are telling yourself, if I act sinusoid with a sine wave on the mass, chances are the mass will respond also with a sine wave. A system like this, you will not basically shake him sinusoidally and then he will basically move and then stop and then move again. There will be no discontinuity, there will be no jerking in it, right? He will just have to oscillate also. But maybe he will be lagging behind you, right? Maybe the magnitude will not be the same. Maybe he will have a little bit of shift. So anyway, he's basically saying that this is the shape of the solution. So if I plug this in here, I will just have to differentiate this. That's fine. I know how to differentiate cosine and sine. Twice for here, one time here, and this guy here, and make this equal to this. So those basically would be equal to this, and from comparing the right hand side to left hand side, you'll be able to put your hand on the an and the bn. So it turned out that the n and an and bn they should be function of what's on the other side, which is n. They're basically a bunch of n's. Okay?
So that 4 over pi, is that specific to this solution?
Say that again.
That 4 over pi, like the r of n up there, is that specific
4
to
over
this
n,
solution?
the 4 over n squared pi, this
Yeah.
one?
Is that
Yeah, this come from the from the Fourier expansion of our R of t. So different R of t will end up in different Fourier expansion. But the point is, it will be cosine. It will be sine. It will be a sinusoidal. So if you have an input like this, you should expect the output to be also in that form. To be sine plus cosine. And by basically plugging that form, again, you are not forcing the solution. You're just forcing the shape of the solution. Alright? And you have the right to do this because you know that's a linear system. The input is a bunch of cosine. Therefore, the output should be a bunch of sine and cosine. Alright? So you get the an and bn, and you add. For every n, there is an and bn corresponding to it. And the y is adding all of them. Okay, so he managed to do this and get the constant, and so for this input, this ramp function, kind of, the output go like this. Does this make sense? So that's very powerful when you have different periodic input function. You split them into sine and cosine, and you have the solution for each one of them, which would be basically adding all of them. That's the solution for the complex input that you have. Alright? Very good. We'll jump to 11.9 and finish this chapter by this. So 11.9, that's the Fourier transform. So when you look to this guy, integrating from minus infinity to infinity, f of x e to minus I wx. So this transformation take you from the x domain to the frequency domain, the W domain, right? And this look as if it's the expansion, the Fourier expansion, huh? And the E is basically the cosine plus I sine omega x. So we'll see that it's kind of the limit of the Fourier expansion. But basically this is a Fourier transform. It's in concept it's similar to the what? Does this remind you of anything beside the Fourier expansion? Laplace. It's the same concept of Laplace. Rather than e to minus st, and let's do the integration, it's e to minus iwx. Again, integrating from minus infinity to infinity. This will take you from, again, the x domain to the w domain. And so rather than small f of x and capital F of s in the Laplace, this time it's small f of x and f of hat of w. And taking the Laplace is replaced by taking the Fourier. So I'm trying to make a capital F and still trying to make a wiggly thing. In our book it look so different book make them differently, but basically they had this kind of weird F thing. So just try to make a weird F with a weird F with also kind of italic into it. Huh? So it shouldn't be a normal F. It should be like capital and kind of going back and forth and come up with your version of it. Okay. So taking the Fourier is basically doing that integration. Let's get f of x multiplied by this guy and get the transform, right? So this is taking the Fourier and this is taking the inverse. So f of x would be basically the difference between them is e to minus I, e to power plus I. So instead of minus iwx, it's iwx. dx, dw. F of x, f hat of w. So this is how you can come up with the Fourier transform. This is how you can come up with the inverse. Okay? Go to the frequency domain, coming from the frequency domain. So, how, for example here, he say, well, f of x is basically this guy. It's 1. Huh? And it's 1 only between minus 1 and 1. And after that it's 0. So 1 here and 0 over there. Outside, and you want the Fourier transform of this f of x. So f of hat, f hat of w is what? Let's get f of x, put it here, integrating from minus infinity to infinity of this guy multiplied by e to minus iwx. Well, yes, I'm integrating from minus infinity to infinity, but the function itself die everywhere except, right? Except from minus 1 to 1. So that's why the integration only survived from minus 1 to 1. And the integration of e to power ax dx, don't worry about the I. Think about the I, it's square root of minus 1, but just think of it as, when it comes to that integration over x, this is simply e to power ax dx. What's the integration of e to power ax dx? It's e to power ax divided by the a, not the ax, just the a. So that's why the minus iw. Alright? And you put the limit and you get the integration. Okay? So for something like this would be the Fourier transform of it. Alright? And here is another example. I don't see anything new. It's simply, well, f of x is e to minus ax. You just put it here, multiply by this. Of course, you know when you have e to power ax plus e to power multiplied by e to power bx, what do you get? E to power a plus bx, right? So that's what you see over here, e to minus ax, e to power minus iwx, you get a plus iw. And again, you are integrating this, it's simply e to power ax over dx, then the integration is the same function divided by the power, right? So what is the big deal about this Fourier transform? What is the cool thing? You know, why we are doing it? Yes?
Is this finding like a filtered signal wave?
So this is basically transferring the function from the t domain or the x domain to the frequency domain. It's simply doing this integral will take you over there. So why are we doing this? What is the benefit behind doing this transform? There are two benefits that you'll see right now. One of them is, remember the convolution? That is this like weird integration. And instead of doing this weird integration, f of b g x minus p dp, or if you remember, we had it where? In the Laplace? It was f of t g t minus tau, t tau, remember? And we said we don't want to do this integration. So it was suggested at that point that the Laplace has this cool feature that integration, if you take the Laplace, what will happen? It will become the multiplication of the Laplace. It's become f of s times g of s. So rather than doing the integration in the time domain, you actually take the Laplace of each one of them, multiply them in the s domain, you have the solution, take the inverse and back it up, back it back to the t domain, right? And so, because the Fourier transform is almost the same like the Laplace, the convolution of those two functions when they are like this, it's basically this weird thing that you are seeing over here. That's basically the Laplace of the the Fourier transform of the first function multiplied by the Fourier transform of the second function, multiplied by square root of 2 pi. Why the 2 pi? Because he's basically the Fourier transform is defined with 1 over square root of 2 pi. It's not simply like Laplace when we did just e to minus st f of t. You had the square root of 2 over pi.
So the square root of 2 pi will always be part of that.
Right. So, but the point is, see that now the convolution, the Laplace of the convolution, the Laplace of that integration, the Fourier of that convolution is basically the multiplication of the Fourier of the transform of the first one times the Fourier of the second one. All right. So this is actually what I do in my own research. So all that we do like spray diagnostics for the Air Force when they had this fuel injection in the scramjet engine, and we would like to figure where are the spray and whether we did a good job, whether that injector did a good job distributing. You don't want all the fuel to be sitting in near the wall or near one place, because that place will melt and you will not have uniform distribution. So you want to make sure that the fuel go everywhere, kind of. Some places you want it in a certain place. Anyway, you would like to find out where are it is. So we make holograms, 3D images. So the hologram is basically, when you record the hologram on the camera, it will actually go like this. It will be a picture, black and white picture, with bunch of dots. Imagine this is actually the hologram of a knight, a chess knight. It will look like this. You don't see anything, because in order to reconstruct the image, to get the image from, so that hologram is interference between two laser beams, two light waves. One of them is reflecting from the object, so I shine a laser beam on Chen and come back to me, and then I have another laser beam coming straight from the source. When they add to each other, they become big and or much brighter, and when they are out of phase, they subtract and they get dimmer. So I get basically a picture of him that superimposed on the reference picture. And so that is the guy who came up with this idea. Actually got Nobel Prize in 1960 something. Okay, he was from Hungary. And the point is that our camera, our eyes are only sensitive to the intensity of the light, right? Dark, bright. I can see his eye pro, I can see his skin, but I cannot see his 3D image. I cannot see that his nose is actually a little bit up. I see because my two eyes, but with one eye I will not, right? So with one eye I have no idea whether his nose is at the same line with his eye or a little bit back or forward. So when you add this interference, you get this 3D image. Short story is the actual reconstruction is in this integration. That integration is a convolution. So rather than doing that integration in the time domain, it's time consuming, we take the Fourier of this image and the reference image that we have. We take the Fourier of the two of them, multiply them, and so MATLAB or any software, when you actually have two matrices, you multiply them, that's piece of cake. You do the multiplication immediately, and then we take the inverse. Alright? You could say, but the time that you spend on the inverse, that's integration too. It will almost be the same time that you are trying to save by not doing the convolution to start with. Where is the saving? Well, the saving came from this. So there is something called the fast Fourier transform. So to start with, there is something called the discrete Fourier transform. So the discrete Fourier transform is basically, rather than doing that integration, which will take us to the frequency domain, this is the Fourier transform. This can be approximated as this expansion. You know how, we did already trapezoidal rule, remember, in the integration, numerical integration, and you can see how this is approximated as this, right? It's as if really you are doing the trapezoidal rule. At different points, you are getting the f of k, not the continuous function f of x, right? So why do you do this discrete transformation? Because the image that you're recording on the camera, or the signal that you are hearing on the mic, most of the time it's not the blue function. It's not the continuous function. The image that the camera records is not a continuous picture. It's actually the red points. It's the digitized point. The camera is a bunch of pixels. The mic is, or the digit recording we are recording at bits. So we are having discrete points, and we would like to get the Fourier of the red points, not the continuous function. So that's why we don't have a continuous f of x. We have a discrete f of k. f0, f1, f3. After every second or every microsecond, what's the function? Or in case of this, those camera pixels are sitting 7 micrometers apart from each other, and each one of those pixels are basically saying it's very bright, it's very dark, they actually have numbers. As a matter of fact, when we look at those pictures, we don't look to the actual picture, we look at the number representing them. You know how in the Matrix, the movie Matrix, they were looking at the world through those numbers? So also when we are looking at the images, we don't look to the actual image of you, we just look at the numbers. Especially because if one of the pixels get very, very hot, or basically very, very bright, he could burn. So your eye is basically watching if the number hit the max is like, say, 4095. So if the number basically hit max on one of those pixels, you know that the light is too much, let's reduce a little bit the signal. My point is that the image is a bunch of discrete points, right? And so that's why we will not be able to do this integration, but instead we will do this summation. And now you can see how this is what? E to power minus I n x. If you split this to cosine plus I sine, then you realize that the Fourier expansion is basically the discrete version of the Fourier transform. Alright? And so this discrete Fourier transform is simply just let's do it over points rather than do it over a continuous function. Okay, so I can give you basically, and there's an example in the book where he give you basically discrete value of f0, f1, f2, f3, 4 points, not an f of x, and he tell you find the corresponding f of n. Again, this is a function and this is a function when you do the integration, but this is bunch of points, and this will end up being bunch of points too. It's discrete values. So for 4, 5, and 7, that was the signal. What is my frequency? Okay, what is the value at different frequency? So you will do this. So now an easier or a quicker version of it is called the fast Fourier transform. That's what we use. And so to do this, it reduces the number of calculation by basically as long as the number of series is multiplication of 2. Then this happened very quickly. All right. So because of this, we actually chop the picture to make sure that, if the picture is like 3000, we don't like it. We would like it to be 2048. All right. We make sure that it's basically, and the difference in the speed is really, really big. So over here, he basically say it go from order n squared to order n log 2 to power n. So it basically go really pretty quickly.